Directed versus random. When it comes to verification, we always need to think of finding bugs. Then the important question is how fast we can find bugs. That's where random test cases come into picture. When it comes to finding bugs, random test cases will always be powerful than directed test cases. Let's look at this example. It's a huge multiplexer. There are 1000 plus inputs and each input might be a bus, more than 64 bits. There is a select bus and there is output bus. So based on select, the output will get a particular input. That's how the multiplexer works. Here the difference is complexity. It's a huge multiplexer. And let's assume that there are 4 bugs lying in this multiplexer. One is at 231, the other one is at 450, the other one is at 749, and the last one at 996. There are 4 bugs. During simulation, we should be able to find all these bugs. Let's start off with directed test case. How this is going to work, we need to analyze. In case of directed test case, what we do, we generate the values in a particular sequence. So for select, we would be generating values like 0, 1, 2, 3, and it goes on like this: 10, 100, 200, 300, 400. That's how it's going to happen. But it will be time consuming. To generate all possible values, we have to spend time. Let's assume that it takes 1 hour to generate 100 values. Then to reach 200, we need to spend minimum 2 hours. So we are going to generate values like this: 0, 1, 2, 10, 20, 30, and then 100, and then 110, 120. It goes on like this. We have run simulation for more than 1 hour. The question is, did we find any bug? And in this case, how many hours it would take to reach all possible values? It's going to take more than a week time. But no one is going to give a week of time to verify a simple multiplexer. Maximum you may get 8 hours. So within 8 hours, how best we can find all possible bugs? So in case of directed test case, obviously it's going to be time consuming. It's going to take a week of time. So we won't be able to verify the multiplexer completely. Let's look at the other possibility, a random test case. When it comes to random test case, we want to generate constrained random values. We don't want to go with pure random. If you look at pure random, what would happen is the values will be generated randomly. We might not even hit the bug. Whatever happens in case of directed test case, the same thing might happen. So we are not really sure about improving the probability of hitting the bug. That's what important for verification. So we want to move on with constrained random values. How can we do that? Look at this. Before generating values, we want to define the bins. So here there are 10 bins and the bins will be defined like this. For 100 values, there will be a bin. So B1, 1 to 100, B2, 101 to 200. So like this, there are 10 different bins for the entire multiplexer. So here, by defining bins, we take care of the data distribution. And for each bin, we want to generate random values. This is how we can improve the data distribution. Now look at how it happens. Test case 1. We are generating 10 random values per bin. So it's going to happen like this. 10 random values for each bin. And we might hit a bug. We might. Suppose we are not getting the bug, then we might want to increase the random values. That's how we do. We run simulation and we look at whether we need to redefine the number of values. Or sometimes we may want to redefine the number of bins also. It depends on how much time you have. Within 8 hours, we can think of creating 10 bins and we can think of generating random values for each bin. Suppose we get 2 days of time, then we can think of increasing number of bins up to 20 or 30. We can think of increasing number of bins. At the same time, we can think of increasing number of values. Now for test case 2, same 10 bins, but this time we are going to generate 20 random values. So we are doing it, and we might hit the other bug. But when it comes to finding bug, it's not going to happen sequentially because we are dealing with random values. So we need to come up with test case strategy, how many bins we want to have and how many random values we want to generate for each bin. That's how we take care of data distribution. And we need to run the simulation. During simulation, we need to check whether we are getting any bug. If we are not getting any bug, then we need to change the approach. We might want to increase number of bins or we might want to increase number of random values. For each test case, this is how we are going to change the strategy. For test case 3, we are increasing the random values further, 30 random values for each bin. And this time, we might hit this bug. Now we move on and increase the number of values. And the generation happens. This time, we might hit this bug. So this is how we would be able to find all bugs. But in any case, we might not be able to assure that, okay, using random test cases, you can find all kinds of bugs. So during simulation, what we do is, we always think like how fast we can find bugs. If we find more number of bugs, that increases the quality of verification. So we always need to think of finding more number of bugs. Can we find all bugs? We cannot assure. Because in any case, the verification is not going to happen in idealistic way. Nobody is going to give you a month of time to verify multiplexer. If that is the case, then probably you might be able to assure 100% verification. Nobody tries for 100% verification. And when it comes to doing this kind of simulation, we focus more on design functionality. Whether the multiplexer has been implemented as per specification. Whether the functionality is retained in multiplexer. That's what we try to prove during simulation. But while proving, we also look at, are we getting bugs? That's how the simulation happens. Now let's discuss about constraint random coverage driven verification. Look at this example. This is DUT. It's a router. It has input channel and it has multiple output channel. Whatever the packet we send to the router, based on the address, the packet will be sent to one of the output channels. That's how the router works. It has one input channel and 3 output channels. And for each channel, as per our test bench methodology, we need to connect driver and monitor. You remember, we need to connect driver and monitor. Similarly, for all the output channels, we have connected driver and monitor. So here, driver 0, monitor 0, driver 1, monitor 1, driver 2, monitor 2. And what we have done, we have connected the generator with all the drivers and we have connected the monitors with scoreboard. This is how we build the test bench. Here the important thing is we need to define the coverage goal. When to stop the simulation is the question. That's where the coverage model becomes critical. Look at this coverage goal. During simulation, I am planning to generate different kinds of packets. In this case, 4 different categories. One is small packet, the other one is medium packet, the other one is big packet, the other one is corrupt packet. And I want the packets to come out of all the channels. There are 3 output channels, channel 0, channel 1, channel 2. Here you look at channel 0, channel 1, channel 2. So 4 packets, 3 channels, and if I consider all the combinations, 4 into 3, 12 combinations here. So I have 12 bins. And when to stop the simulation? If I can fill all the bins with all the values, then the coverage will be 100%. What it really means is, during simulation, I want to generate all kinds of packets: small packet, medium packet, big packet, and corrupt packet. I want to generate all kinds of packets, and I want to drive all kinds of packet to the router, and I want to make sure that all these packets will come out of all the channels. If this happens, I can confirm that the router works fine. That's what the coverage model indicates. 12 combinations. If I can generate all kinds of packets, and if I get all kinds of packets from all the output channels, then I can confirm that the design works fine. Let's look at how this constraint random coverage driven verification works. So here on x-axis time is nothing but wall clock time. Are we going to spend weeks of time for simulation or months of time? That's what the time means. And on y-axis we plot coverage. So here the goal is 100% functional coverage, and when I say 100% functional coverage, we need to fill all these bins. Small packet should come out of channel 0, small packet should come out of channel 1, small packet should come out of channel 2. Then I should get medium packet from channel 0, from channel 1 and channel 2, and big packet from channel 0, channel 1 and channel 2, and corrupt packet also, at least one corrupt packet from channel 0 and from channel 1 and channel 2. If I get all kinds of packets from all the channels, then I can confirm that the design works fine. That's called 100% coverage. So the entire simulation is going to happen based on the coverage model. This is going to be golden reference. That's why it's called coverage driven verification. As we deal with constraint random stimulus, we discussed about constraint random. This methodology is called constraint random coverage driven verification. Look at this, CRCDV, which means constraint random coverage driven verification. All right, let's look at how the simulation is going to happen in phases. It starts with trivial verification. So trivial verification means we have to build the test bench. We need to verify the test bench itself. So basically we make the environment stable. This is called self-checking random environment development time. How much time we are going to spend to bring up the environment. When it comes to making the environment stable, what I would suggest, we need to generate one small packet, and we need to make sure that the small packet will be generated properly by the environment, whether it will be driven properly by the driver, whether the same packet will be collected by the monitor, whether we are getting the same small packet from the DUV also, but that's going to be binary value, and we might want to convert the binary value back into packet. So we need to make sure that the entire data flow happens properly with one small packet. That's how we can bring up the test bench. It's a detailed process. So basically what we do is we write the source code for every component: generator, driver, monitor, scoreboard. There will be different kinds of components, and we connect all the components with the help of mailbox. And then once we put all the components in the environment, it's not going to work as you expect because the environment is going to be complex. You try to recollect the example which we discussed, the router example. In this case, multiple drivers, multiple monitors, there will be too many connections. So the environment is not going to work as you expect. It's not going to happen easily. So then we need to bring up the environment. We need to generate some stimulus for the environment itself, and then we need to verify thoroughly whether the environment works fine with one small packet. That's called trivial verification. Let's say it takes 1 day for a small design, but we cannot consider the time which you have spent for test bench verification for the design verification, because during this verification the coverage will be 0. We haven't verified any of the DUV features. What actually we are doing is we are verifying the test bench itself. In case of complex test bench, the test bench which we create for SoC, system on chip, it might take even a week of time also, but that 1 week will not be considered for design verification because the coverage is 0. So during simulation, the focus will be more on filling the bins. Are we getting coverage? That's the important question. So during trivial verification, the coverage will always be 0 because we are verifying the test bench. All right. Now, once the test bench becomes stable, then the focus will be more on generating random packets. Look at here. So the next phase is called broad spectrum verification. What is broad spectrum verification? We implemented the verification environment based on the architecture. We verified the environment with the help of one small packet. Now the environment is stable. It works fine. It works beautifully. Once we gain the confidence that the environment works fine, there are no issues, all the connections are proper, then we can think of generating hundreds of packets. That's called broad spectrum verification. So in this case, the coverage is going to shoot up to 40 to 60% quickly, maybe within a couple of days. That's the advantage of system Verilog. So in case of system Verilog test bench, initially it might take time to produce the coverage, design coverage. But once the test bench becomes stable, then the coverage will shoot up. So in broad spectrum verification, we try to reach as much as possible. So here, if you look at during broad spectrum, most of the bins will be covered. During broad spectrum, the focus will be more on randomizing the stimulus. So we will try to run the test case with different seed values. That's how we would be able to generate different kinds of random packets. Look at here. This is going to be an iterative process. This circle is going to continue. We generate random values. We run the test case multiple times with different seeds. And every time when we run simulation, we look at coverage, how many bins have been covered, and which are all the bins remaining. It's called as coverage holes. And based on coverage hole, we include some more constraint. It's called code modification. We fine-tune the constraint. It's called constraint random coverage driven verification. So we add constraints and then we come up with new test case. For the new test case, we try different seeds and we check whether it's improving the coverage. We try to reduce the coverage holes. So this is how it's going to continue. We generate random values. So we run the test case with different seeds. That's how we generate different kinds of random values. And for each random value, we generate functional coverage. And based on the coverage model, we look at okay, how many bins have been covered and which are all the bins remaining. They are called as coverage hole. And based on the coverage hole, we fine tune the constraint. Okay, in this case, how the constraint is going to be. I covered almost 50% of the bins, and based on the remaining bins, we will redefine the constraint. For example, in case of multiplexer, the values would be 0 to 1000 plus. So in this case, we covered 0 to 500. Then we want to exclude this subset 0 to 500. We want to focus only on 500 to 1000. That's how the new constraint is going to be. And within 500 to 1000, we try to randomize as much as possible. That's how the simulation is going to continue in broad spectrum. And then we get into corner case verification. When I say corner case verification, we have to really look at how to improve the coverage further. Once we reach certain level like 60% or 70%, it won't improve quickly. Then we may want to analyze the stimulus itself. Instead of generating only small packet, big packet and corrupt packet, can we try the combination? Maybe 100 small packets, 10 big packets and 1 corrupt packet. If we send the sequence to router and how the router is going to behave, that's called corner case verification. That's how we can define new test cases. That's how we can improve the coverage further. So the coverage will be improving like this, from trivial verification 0% to 40% and then 40 to 60 and then 60 to 70. And then we need to try different combinations, different scenarios. That's how the coverage is going to improve further. Then it will reach a particular saturation point like 95%. Once you reach that saturation point, the coverage will not improve irrespective of whatever the strategies you create. That's called saturation point. So in this case, if you look at, the corrupt packet is not coming out of channel 1. We have randomized the packets as much as possible. We got almost all the combinations, but one combination is not happening. The corrupt packet is not coming out of channel 1. This one combination is not happening. Then in that case, stop random simulation, generate corrupt packet manually and make the address in such a way that it comes out of channel 1. So we are going to fix everything, and that would be very similar to directed test case. So we generate corrupt packet, we make the address for channel 1. So when you send this packet, automatically it has to come out of channel 1. It's called directed test case. So you generate that particular combination and reach 100% coverage. The coverage closure will always happen through directed test case. But the guideline is, you are not supposed to switch from random to directed when you are at 80% or 60%. You need to make sure that you reach the saturation point. The saturation point would always be like above 90%. There could be few combinations pending. When you feel that there is only one combination that's pending, and I have been randomizing the stimulus, but still I'm not able to hit this combination, then you stop the random simulation, you switch from random to directed test case. That's how you would be able to reach 100% coverage. All right, look at this. So you are done with corner case verification. You try different combinations. Now in this case, you switched from random simulation to directed test case, and that's how you would be able to reach 100% coverage. This is called directed verification. The entire process is called constrained random coverage driven verification. As we deal with constrained random stimulus, it's called constrained random, and as we use coverage throughout simulation, it's called coverage driven verification. It goes through various phases like trivial verification. During trivial verification, we verify the test bench, not the design. And once the test bench becomes stable, we would be able to generate different kinds of random values and increase the coverage value quickly. The coverage will shoot up to 40 to 60%. And then the coverage will not improve easily. So we may want to think of different kinds of combinations, like small packets, big packets and corrupt packet, all kinds of combinations. That's how we try to verify the deep state of the design, and that's called corner case verification. And once you reach the saturation point, the coverage will never improve. And once you realize that, then you may want to switch from random simulation to directed test case. That's how you would be able to reach 100% coverage. This is called constrained random coverage driven verification. The simulation is going to happen like this. At the top, for every test case, we would be generating different random values with different seed. So for every test case, we run simulation with different seed values. So with the help of seed, we would be able to generate different kinds of scenarios. This is how the simulation is going to happen. And for each packet, the coverage will be generated. So throughout simulation, we would be looking at the coverage progress. Look at here. And once we reach 100% coverage, then we will stop the simulation.